Hello again. This is Math 2232 coming to you from the College YouTube page. The title of this lecture is Areas with Parametric Curves. As always, please be attentive while watching this video. By way of introduction, one of our learnings from calculus was to find the area between a curve and the x-axis. Although one could certainly, and maybe perhaps is a better word, eliminate the parameter in a parametric curve representation and compute such an area in rectangular xy coordinate settings. A natural question is, can we do this parametrically? The answer is yes, and invariably it is more efficient to do so. So, in this lecture, we will discuss how to find the area between a parametric curve and the x-axis using only the parametric equations, rather than eliminating the parameter and using standard calculus techniques on the resulting xy algebraic equation. So let's begin with parameterization. So we'll let x equal lowercase f of t and y equal g of t. Now we do have to restrict things because these curves can be very complicated and cross each other. So the curve is traced out exactly once as t increases from limits alpha to beta. And these are limits on t. Now we will do this in much the same way that we found the first derivative in a previous section. We first recall how to find the area under curve with x and y. So this, as an example, we will say that y is equal to capital F of x on the interval, and this x runs from a to b. And in that case, the area could be found to be equals simply the definite integral from a to b of capital F of x dx. Now we've got a parametric representation though, so we're going to let x be lowercase f of t in this interval. It's a change of variable, and this is a substitution in the integral. And we're going to assume that a, because we have to be mindful of the limits when we do this, a is equal to f of alpha and b is equal to f of beta, and these are both lowercase f's. That's the same f that was in our parameterization for the purposes of this formula. And there's no reason to assume that that will always be the case, so it could be the other way about on the interval. So b could be f of alpha and a could be f of beta. So what we know though is that if x is equal to f of t and lowercase f is differentiable, then dx is equal to f prime of t dt. So if we plug that into the formula above, we get that. Now we're integrating t, so we're going from alpha to beta, but the area is equal to, this is capital F of lowercase f of t, and this is f prime of t dt. Now, since we don't know what capital F of x is, here's what we know, that y is equal to capital F of x, but that is equal to capital F of t, and you see that was y, so y in our problem is equal to g of t by the initial assumption. So we arrive at a formula then. The area under a parametric curve, and I'm going to call this formula 1, is that a is equal to the integral, and this is the integral dt, the parameter, as t runs from alpha to beta. This is g of t, which is what y is, times f prime of t dt. You want to think about this a little bit, and if the formula worked the other way, the limits would perhaps be reversed, but the formula looks much the same. Think about this, please. And let's do an example. Determine the area under the parametric curve given by the following parametric equations. So x is equal to 6 times the whole of theta minus sine theta, and y is equal to 6 times the whole of 1 minus cosine theta, as theta runs from 0 to 2 pi. Now, this theta is just a variable, so it's like t, And so we're treating this just as a variable. It's a variable, a real variable that runs from 0 to 2 pi. You know what to do. Let's see how you did. And by the way, before we do that, let's look at what the heck does this curve look like. And so I've graphed it here. So you see it goes up like that. And it goes pretty high up here, a little better than 12. You see the cosine sometimes is -1. So -1 minus -1 would make the y component 6 times something that's around 2. And so, that's why we get up here close to 12. And you see that this is a curve that's looks like that. And you might say, well, why should I care about this curve? Well, we'll talk about that in a bit, but let's look at the solution first. So we have x equal 6 times theta minus sine theta, and y be this, and so on and so forth. So we have to change variables. So we're going to say that dx d theta is equal to, and I take the derivative here. The 6 just sits there. I get 1 minus, and this is going to be cosine theta. So that is what dx d theta is. And y is 6 times 1 minus cosine theta. So the area, then, if we substitute in the formula we derived before, is going to be the definite integral from 0 to 2 pi. 6 times 6 is going to be 36. And 1 plus cosine theta times 1 minus cosine theta. Actually, I was lying with that. This is 1 minus cosine theta times 1 minus cosine theta. And so that'll be 1 minus cosine theta whole squared d theta. And so that's what we get. Now we need to do some algebra. We expand this, and we again, it's going to be taking 1 minus cosine theta times 1 minus cosine theta, and we get, I'm going to pull the 36 out. So we get 1 minus 2 cosine theta plus cosine squared theta d theta. And so now what we're going to do is we can integrate this. And by the way, if we do the trig identity, and the trig identity that we're doing here is the standard one for cosine squared theta. So cosine squared theta is equal to 1/2, and then it is going to be 1/2, and then it is plus 1/2 cosine of 2 theta, and that's either the half angle formula or the double angle formula. And you see we've got a half that we get from this, so the half combines with the 1 to get 3 halves. And so this is just some algebra that we do, but now we've turned this into something we can integrate, cosine 2 theta, and so we do a u substitution, and so we go through, and we're going to get 36 is on the outside. This is going to be, since this is 3 halves, at the end of the day, this is just going to be 3 halves times 2 pi, because a constant integrated over an interval is the constant times the length of the interval. The antiderivative of the cosine is the sine, and this we change variables. We have to do the 2 theta and theta dance, but we do that and we get this. And then we evaluate this at 2 pi and 0. Now I would expect you to be able to do this pretty much without a calculator, but if we plug those numbers in, and you should check, but we get 108 pi. Now, the parametric curve that we were talking about without the limits that we used in the previous example is one that is a very famous curve. It is called a cycloid. In the general form, where we're letting the thing that was 6 be r, so this could be a different kind of circle, we would have x is equal to r cosine r theta minus sine theta, and y is equal to r 1 minus cosine theta. Now the r, we could think about that as being a parameter, but it's not. It's a constant. It's just saying what's the size of the circle. So there's actually one parameter here. It is theta, or we could call it t. Now if we look at the graph of that, and I looked at part of the graph of that, and we'll look at some more down here below. So the cycloid represents the situation where we have a wheel of radius r, and let the point be where the wheel touches the ground initially be called P. So here is P, And we put a little dot there if you want to think about that. Then start rolling the wheel to the right. As the wheel rolls to the right, we're saying what happens to P. So you see P would start going around like this, and so what is happening with P is it's getting higher and higher, and then it goes up there, and then it goes down. You might want to experiment with this just a little bit. You could use a coin and a little blue magic marker to think about how this works and convince yourself that this is what happens. So I go like this, but then it hits the bottom, it's back where it started, so I'm going to do that again, and I can do that again and again. So the path that the point P traces out is called a cycloid and is given by these equations above. And we think about theta as the angle through which the P has rotated, the point has rotated. Now here's a cycloid sketched out for the wheel at various points. The blue dot is the wheel that we're seeing to trace out the curve. And so you see that what we were talking about before was one arch of the cycloid is traced out from 0 to 2 pi. And so that's what we have. Now you might say, okay, that's interesting, but it actually is very interesting and has been for a very long time. The cycloid, in fact, has been called by some the Helen of geometry, after Helen of Troy, not only because of the beautiful properties, and I could teach an entire course on the cycloid, but also because of the quarrels that is provoked between famous mathematicians in the actually 15th through 17th century. The cycloid was first studied by Nicholas Cusa. He was a German polymath, actually, and he was attempting to find the area of a circle by integration, except integration hadn't been invented yet. In the 1600s, the 17th century, the French, he was German, he is French, the French monk Mersenne gave the first proper definition of a cycloid. This was in words, and he stated the obvious properties such as the length of the base equals the circumference of the rolling circle. You might want to think about that. Mersenne also attempted to find the area under the curve. Again, he was trying to do this before calculus was invented by integration, but he failed. This is a problem that you just did. But back in the day, a great mathematician couldn't do it. He posed the question to other mathematicians. The great Galileo named the curve in 1599, and he wrote to another great engineering person, mathematician, Torricelli, about the cycloid, saying they'd been studied the properties for 40 years. There was a lot of intellectual capital here invested in this by Galileo. Galileo attempted to find the area by comparing the area to its generating circle, and he failed at that to find the mathematical method. And so he resorted to sort of guessing. Now he found that the ratio of the weights was approximately 3 to 1, but he said that's not. But he decided it was not exactly 3, and in fact he guessed wrong. The ratio is not rational. Mersenne proposed the problem of area to Roberval, and although he failed at first, he solved it in 1634. And got that the area under an arch is 3 over pi a squared, where a squared is the radius, and that's similar to what you got on the problem that we talked about. He was proud of his result, and he wrote to the great mathematician Descartes, telling him of this. And Descartes replied, "This is a pretty problem. It's a pretty one, which I had not noticed before, but which would cause no difficulty to any moderately skilled geometer." Descartes was a little strange, but anyway, that was his response, and he is very famous. And he challenged his colleague to find a method of drawing a tangent, which was the idea behind the derivative, to the cycloid. And he had discovered how to construct one. And so Roberval failed, but Fermat, the great mathematician of Fermat's last theorem, was included in the challenge, and he succeeded. It was worth noting that Torricelli independently discovered the area of the cycloid, and that this fellow, Vivani, found a method for constructing a tangent. There's a lot of Hall of Fame mathematicians that are being mentioned here, and you solved a problem that they didn't know how to solve. You might say, oh, that means I'm pretty smart. Well, you might be pretty smart, but you've also benefited from all the people who've developed calculus before you studied it. The story goes on, though. In the 17th century, Pascal, the great French polymath and mathematician, after a long spell devoted to religion when he ignored mathematics, started to think about mathematical problems again as he lay awake at night, unable to sleep because he had a toothache. He solved the problem and his toothache went away, and so he thought God wanted him to do math again. So he found the area of any segment of the cycloid and the center of gravity of this. That was like the center of mass that we study in, back in the center of mass and moments things. He also solved the problem of the volume and surface area of the solid of revolution. See, these are things we talked about, formed by rotating the cycloid about the x-axis. Now, he did a challenge and he offered 2 prizes for solutions. And again, these are very famous people who did it. One very notable person, Christopher Wren, was a great architect. Many of the buildings that Christopher Wren designed in Europe are still standing. And he was a prominent member of the Royal Society, and he found the arc length, and we're going to be talking about arc length. In fact, we've already talked about arc length, but he found it parametrically, and so, we end up with that. And so it just goes kind of on, and it even includes the Bernoullis, who ask what curve satisfies the Brachistone property. Now, this is property saying that, gee, if you want to have a shape of a curve that something will roll down fastest from point A to point B due to gravity, he wanted to know what would the curve be. Now, he already knew that this is related to the cycloid, and it was also shown by Leibniz, Newton, Bernoulli, and L'Hopital. The story is that Newton came home after a hard day of work. He found the challenge problem. He ate dinner, went to his library for about an hour, wrote up the solution, and sent it off. Newton was a giant. So anyway, that's a lot of history behind this curve. Now you might say, yeah, but I don't care about this history. Well, as an engineer, you should, because this is a very stout geometrical construction. This is a catenary, or not a catenary, excuse me. I meant to say this is a cycloid. And this house has multiple cycloids in it. This is an architect that put that together. And the inverted cycloid, which is the problem that Bernoulli posed, you see this is an upside down cycloid here. And this is also an upside down cycloid. So you see, if somebody's wanting to do skateboarding, this is the ideal shape to have. Very important from a construction, architecture, and even engineering standpoint. In closing, now more than ever, time is precious. Each day must count. Do the math, it will make you strong. And now, more than ever, take care of yourself and of each other. May God bless you all.